Hi, this is a new video in the lecture series Digital Economy and Data Analytics. My name is Ivan Vuren and today we're going to look at the new topic, and that's the topic of classification. Remember that in machine learning, or better to say supervised machine learning, there are two types of supervised machine learning. That is, on the one hand we have regression, and on the other hand we have classification. Regression means that the outcome variable is going to be a continuous outcome variable. It's a continuous stochastic variable. And with respect to classification, it is the case that the outcome variable is going to be discrete. That is what it means actually, the difference between regression and classification in machine learning. So far we have only been looking at regression analysis. So today what we're going to do is that we're going to look now for the first time at classification. In order to explain classification, classification implies that the outcome variable y takes one of c different outcomes. This is typically called classes, so that is the terminology that we use at the moment that we're going to use machine learning. Well, it's simplest to think of the case in which the support of y equals 0, 1 up till c minus 1. Question of course arises, why do we want to do that? Why don't we want to simply start with 1 and then end with c? Well, the reason behind that is because of the fact that we should realize that the simplest situation of classification is a dummy variable. That implies that we have two different outcomes, one outcome which is equal to 0 and another outcome if something happens, then at that moment in time we have a value equal to 1. And therefore, in order to generalize the idea behind a dummy variable, we usually start with 0 instead with 1, and then of course we also end up with c minus 1 at the moment that we have c different classes. And now the supervised learning problem is now to predict the class for a particular realization of x equal to this little x that we have over here. Well, that's important to realize because of the fact that that implies that our predictor, remember that this was usually called learner. We have gx of course, but at the moment that we're going to estimate that we have g hat x, can only take outcomes from 0, 1 up till c minus 1. That seems to make sense. Why would you want to make predictions, for example, equal to 1.5 or 0.5 or pi or something like that at the moment that we only have as potential outcomes 0 up till c minus 1. But take into account that this is actually quite different from the view that we usually have at the moment that we're going to look at econometrics. In econometrics, we sometimes are going to try to do logistic or probit regression, in which the, say, left-hand side variable is going to be a dummy variable. It can only take values equal to 0 and 1, but take into account that at the moment that we typically are going to predict in econometrics, then we do not predict whether something is a 0 or 1, but instead what we usually predict then is that we simply are going to say like, what is the probability that we get 1, or what is the probability that we get a 0? And that is not what we're going to do in the case that we're going to look at machine learning. Then we are not going to think about probabilities, but we simply are going to, predict a particular outcome, a particular class. Well, then there are many examples with respect to that. It's actually much easier to find good examples for classification than at the moment that we're going to think about regression, because most of the machine learning or supervised machine learning applications are actually classification and not so much regression. We have already discussed faces in Facebook pictures, so I don't have to say too much about that anymore, but take into account that there are many more of them. We can think of credit worthiness with respect to customers for a loan and a credit card. Take into account that at the moment that you would like to get a loan, or at the moment that you would like to get a credit card, well, especially at the moment that you want to have a large loan as a consumer, for example, at the moment that you would like to get a loan for a car, or even a loan for a house, at the moment that you would like to get a mortgage, then it's typically the case that you have to go, or it used to be the case at least, that you have then to go to the bank, and then somebody at the bank is going to talk with you, and then after a while he or she is going to tell you whether you're going to get the loan or not. Well, take into account that that actually might be very expensive, and it's also in many situations pretty subjective. So therefore you could ask yourself the question whether machines could actually do that better. What does that mean? Well, that means of course that you get a lot of information about a particular individual. You would like to get the income, of course, of the individual, whether the individual has loans, of course, whether the individual does already have loans, what the spending of the particular individual is, and take into account that banks usually have a lot of information already available, especially if it's your own bank, if it's the same bank on which you have a current account, then the bank already knows quite a lot about not just your income, but also especially about your outlays. And all that can be probably used and in a very objective way in order to find out whether it's a good idea to give a particular individual a loan or a credit card. But we can also think of other examples. We can, for example, think of the recognition of handwritten digits. Or more general, we can even think of a situation in which we are going to have recognition of, say, letters in the alphabet. Take into account that one of the things that we would like to do is that we would like to have machines that can actually read, say, handwritten things like digits or, say, the letters in the alphabet. And that implies that, at the moment that we're only going to have digits, it implies that we only have 10 different classes. But at the moment that we also are going to look at letters, well, then it's going to be, at least 26 extra, so at least 36 of different classes. And then the idea is that based on, for example, a picture that is taken of a particular letter, based on a, say, handwritten, of handwritten text, then what we're going to do is that we essentially going to try, in a sense, same way as with respect to the Facebook pictures, but there it's only the idea that you either have a face in a picture or not. In this particular situation, we are more interested in the situation of whether we have an A or a B or, for example, a Z. And then finally, we also have the idea behind heart attack screening. Take into account that that's another example that we have already looked at before. Remember that the loss function for classification is a so-called 0-1 loss function. What was that? Well, remember, of course, that the loss function is always determined by this loss that we have over here, or at least denoted by this loss that we have over here. And then in addition to that, we are going to have two arguments with respect to the loss function. That is, first of all, this y that we have over here, which is nothing else as the realization of the large y, the outcome variable that we would like to predict. And then in addition to that, we also have this y hat, which is going to be our prediction. And we do already know that this loss function is always equal to 1 at the moment that we're going to make the wrong prediction. So in the case that y and y hat, they are not equal to each other, and it's equal to 0 at the moment that we make the right prediction. And that's of course only in the case if y and y hat are equal to each other. Now remember that at the moment that we have been introducing the loss function for the continuous case, for the regression case, then we had this squared loss function. And remember that when I introduced that, then I actually said that then at that moment in time we do already know, at least theoretically, what our optimal prediction function g star x must be. Remember that that was equal to the mean of y conditional on x equal to little x. However, take also into account that that actually doesn't hold now anymore because of the fact that we don't use the squared loss function over here and we don't have a continuous outcome variable, and therefore the g star x that we had before doesn't hold anymore. However, we can now replace it by a new optimal, theoretically optimal prediction function. And that is in this case equal to the argument that is going to maximize, well, over the different classes that we have over here, this conditional probability that we have over here, the probability that y is equal to this little y over here, conditional on x equal to little x. So this means actually in words nothing else as that we are going to predict that class that has the highest well, conditional probability, conditional on the outcomes of the features. Well, we should realize that, well, that actually makes a lot of sense. And the reason behind that is because of the fact that suppose that we are going to have the very simple Facebook example that we had before. Well, then at the moment that we are going to see that the probability of, say, having a face in the picture is higher than the probability of not having a face in the picture, well, then at that moment in time, it might be better to actually predict that we have a face in the picture. So that actually is exactly what we have over here, because of the fact that then it actually maximizes this thing that we have here at the right hand side. The same is of course true at the moment that we are going to look at handwritten digits. At the moment that the probability that we have, say, a 2 is higher than the probability of any of the other digits, well, then it's actually best to, say, predict that we at this moment in time are going to have a digit 2. So that's the idea behind this, say, optimal prediction function. I'm going to say a lot more about that later on, but the fact is that we still have to prove this. And the proof that we are going to have over here goes along the same lines as what we had with respect to the proof that we had in the continuous regression case. That means that, first of all, what I need to do is that I have to write down, well, I'm going to at least define this function hx that we have over here as simply being the right hand side of this function that we have over here. So again, it's going to be the argument that's going to maximize with respect to the different classes this conditional probability that we have over here. Now, of course, the question arises, what do we have to prove in this case? Well, what we have to prove is that the risk function is going to be maximized at the moment that we are going to use this, this particular function that we have over here, this particular function g star x that we have over here. Well, then the first question that arises, what was the risk function? Well, remember that risk function was, of course, nothing else as the mean over the loss function. In this case, our loss function is, of course, nothing else as this thing that we have over here. That's that 0 and 1 loss function that we have introduced already over here. And, well, for, of course, our predictions. And in our case, the predictions are, of course, equal to this gx that we have over here. So this mean, again, we know that already for a long time, is over both y and x. So what I actually now have to prove in the end is that, well, the LG that we have over here for any function d that we have over here is always larger or equal to, well, L evaluated in this function h that we have over here. So what I would like to have in the end is, say, a statement saying that L evaluated in g is larger or equal to L evaluated in h. Then I have actually proven this line that we have over here. The first thing that we then can do is that we can then first of all rewrite this mean that we have over here, take into account that the mean is always equal to an integral, and then we can do here as well. We can now integrate. In this case, what I'm going to do is I'm not going to integrate over both y and x, but I'm only going to integrate over x in this case. And I can do that well by using the law of iterated expectation. So what I can do is that I can now use, instead of the unconditional mean that we have over here, I can use the conditional mean conditioning on the outcomes of x. And then what I need to do is, of course, integrate over the full support of this x that we have over here, that I use here for this Galois x, and we are going to multiply it then either by the density or the probability function of this x that we have over here. Well, then the next step that I can take is that I can realize that this large x that we have over here is, of course, equal to that large x that we have over there, because of the fact that we condition upon it, and we condition on the outcome of this small x over here. So therefore we should realize that this thing that we have over here should also be equal to the small x that we have over here. So that's the next step that we are going to take. And then the next step that I'm going to take is that I'm going to realize that this is, of course, a mean, and take into account that in this case this is a mean over a discrete outcome variable. And we do already know, well, already from I would say high school, that at the moment that we take a mean over a discrete outcome variable, then that is actually nothing else as a sum over the potential outcomes multiplied by the probabilities. Well, in this case, we should realize that that means that we have, of course, the outcomes y that we have over here with respect to this indicator function that we have, of course, over here. So what we can do is that we can sum over all the different outcomes. I use now a small y of that, and well, then we have to realize that then, of course, the large y that we've had before becomes a small y, and we have then to multiply this by the probabilities that y is equal to little y conditional on x equal to x. In this case, conditional on x equal to x, that's of course not completely, I would say, high school mathematics, but that's because of the fact that we have here a conditional mean rather than a mean itself. So we also have to then multiply by the conditional probabilities, of course. So then we have this thing that we have over here. Take into account that we can also rewrite this a little bit because of the fact that well, this is an indicator function, and it implies that this indicator function can only take two outcomes. It is either equal to 0, in the case that y and gx, they are equal to each other, or it's equal to 1, in the case that y and gx are not equal to each other. So that means that what I can do is that I can actually also sum only over those, say, situations for which y and gx, they are unequal to each other. Then at that moment in time, I don't have to write here 1 because of the fact that I do already know that I actually have here a 1 over here. So multiplying by 1 doesn't make that much sense, of course. But in addition to that, there's one other outcome, of course, and that is if y and gx are equal to each other. But then we simply get a 0 here, so then I can completely forget about that. So that implies that the only thing that I need to do is to sum over all those outcomes for which y are equal to gx, and well, then I simply get the probabilities that we have over here. So I can also write it in this format that we have over here. Well, then the next thing that I can do is that I can realize that this actually is equal to, well, this is actually a sum over all the potential outcomes for which y is unequal to gx. Take into account that that is, of course, nothing else as the probability that y is unequal to gx. That's again very simple from I would say high school. You would know already from high school that if you would like to, well, look at the probability that y, or for example, at the moment that you throw a dice, you would like to know what is the probability that you don't throw 6. That's of course equal to the probability that you throw 1, 2, 3, 4, and 5. And that implies, of course, that you can also do it the other way around. The probability that, well, if you sum over all the outcomes for which y is equal to gx, well, that's of course equal to the probability that y is unequal to gx. So you can also write it in this format that we have over here. Another very simple step then is also that we can write this, of course, as the 1 minus the probability that y is equal to gx. So therefore we can also write it in this format that we have over here. Then take into account that this is an integral now over difference. It's an integral over, say, 1 minus this probability of over here. We can also write that as the difference of integrals, but take into account that then the first integral that we're going to get is simply the integral over these ones multiplied by the full density over the full support. That's simply equal to 1 itself. So therefore we can write this as 1 minus the integral of this probability that we have over here. Well, now we are now actually we get to the most important step, and that is that we now should realize that at the moment that we are going to then replace this probability that we have over here by the probability that y is equal to hx. So if we replace this gx by hx, then based on the, well, assumption that we have over here, well, this is actually not an assumption, but that's the definition of hx, because the fact take into account that hx actually maximizes the probabilities that we have over there. So therefore, well, it should be the case that any, say, probability that y is equal to hx, whatever hx is going to be as a function, should be larger than or equal to the probability y is equal to gx, because of the fact that that's the definition. hx actually maximizes the probabilities as we see over here. So that implies that the probability that y is equal to hx conditional x equal to x must be larger or equal to the probability that y is equal to gx conditional x equal to x, because of the fact that that's the definition of hx. And that means that since this is actually true, we should realize that that means, of course, that this part that we over here should be larger at the moment that I replace, or it should increase at the moment that I replace g for h. But that means, of course, that since I have here a minus sign, well, this thing that we have over here is going to be smaller at the moment that I replace g for h. And that means, of course, that this whole right-hand side that we have over here should also become smaller at the moment that I'm going to replace g for h. What does that mean? Well, that means, of course, that the, say, L evaluated in g should always be larger or equal to, well, this right-hand side that we have over here in the case that I replace g for h. So that implies that this actually should always be true. Well, now we are almost done, I would say, because of the fact that the only thing that I now actually have to do is to do, in fact, all the steps backwards in order to get that this essentially is equal to L evaluated in h. So that implies that the first thing that I'm going to do is that I'm going to bring this 1 into this integral that we have over here, and that can be quite easily done by simply now getting this step that we have over here. Then I'm going to realize that 1 minus this probability that y is equal to hx is of course nothing else than the probability that y is unequal to hx, so we can also write it in this format that we have over here. Then I can realize that the probability that y is unequal to hx is of course also equal to the sum over all the probabilities, all the outcomes for which, of course, y is unequal to hx. So I can also write in this format that we have over here. Remember, of course, that the probability that we don't throw 6 is equal to the probability that we throw 1, 2, 3, 4, and 5. So that's essentially what we do here as well. And then we should realize that this can actually be rewritten in this indicator format. What I can do is that I can here sum over all the potential outcomes, but then I need this indicator function that indicates, of course, that y is unequal to hx. And then I can realize that, of course, this is actually nothing else as the conditional expectation of this thing that we have over here. So therefore we can write in this format that we have over here. And then I can realize that this x is of course equal to that x. That one is equal to large x. So I can also write this in terms of a large x. And then essentially using another time the law of iterated expectation, but now actually the other way around, we will find that this is actually nothing else as the mean of this this indicator function that we have over here. But that's actually nothing else as our loss function, now not evaluated in g, but in the function h that we have over here. And that's exactly what we wanted to prove. Well, we should realize again that this thing that we have over here, and in fact, is now going to be very, very fruitful, and actually in this case it's also very intuitive. As I already said, at the moment that you would like to make the best prediction, then just predict that thing that has the highest likelihood of occurrence, that class that has the highest likelihood of occurrence. Take into account again that this is only of theoretical help, like what we have seen before. At the moment that we were looking at the continuous case, the regression outcome case, then at that moment in time we also have been seeing that we had this mean of y conditional x equal to x, but we don't know that mean, we can only try to estimate it. And remember that then all the procedures, all the methods that we have been discussing, like lasso, regression and things like that, they essentially don't do anything else as trying to, well, estimate that conditional mean. Here also, this is only of theoretical value because of the fact that we don't know these probabilities that we have over here. If we would have known these probabilities over here, then at that moment in time we immediately get this g star x that we have over here. We don't have to do anything anymore. We don't need data anymore. But instead, we don't know these probabilities that we have over here in general. And therefore, instead, we are going to use data in order to estimate it. And take into account that that essentially is the whole idea behind classification. We try to get estimation methods in order to estimate this thing that we have here at the right hand side. Well, this results actually in so-called decision spaces of the support of x, because of the fact that we should realize that, well, at the moment that we're going to go back to this g star x function that we have over here, that of course the question whether we are going to predict, say, particular kind of things actually depends on the outcomes of the features. That means, of course, that at the moment that we are going to, for example, suppose that we have here a classification in which we have to predict heart attacks. Well, then at that moment in time, of course, at the moment that a particular individual has different kind of features, say the BMI of the individual or the cholesterol level of a particular individual, or whether the individual is smoking or drinking, well, will actually determine, of course, whether we are going to, well, predict whether an individual is going to get a heart attack or not. That is to say, the probabilities will, of course, change. The probabilities of getting a heart attack or not, of course, change with respect to the outcomes of the features that we have here at the right-hand side. At the moment that somebody has a very high cholesterol level and smokes, and, for example, also has a very high level of BMI, well, then, of course, the probability of a heart attack is going to be much higher than at the moment that we have an individual that is going to, well, actually have a perfect BMI, is going to have a perfect cholesterol level, doesn't smoke and drink. So we should realize that, of course, whether we are going to predict here in this particular case whether somebody gets a heart attack or not, well, does depend, of course, on these probabilities that we have over here, and these probabilities actually depend on, in fact, the outcomes of the features that we have over here. And that implies that what we are going to have is so-called decision spaces, areas with respect to the total feature space in which we are going to predict a particular outcome. So again, we could actually predict, say, for particular kind of combinations of, say, smoking behavior, BMI, cholesterol levels, we might actually predict that somebody is going to get a heart attack, and for other combinations we are going to predict that somebody doesn't get a heart attack. And take into account, of course, that these things interrelate, of course. Maybe just smoking and having a perfect BMI as well as a good cholesterol level may actually not directly result in a prediction of a heart attack, but of course the combination of these things, they actually are going to make that somebody is going to be predicted to have a heart attack and another individual is not going to be predicted to have a heart attack. That means more generally, of course, at the moment that we have C different classes, that we have C different decision spaces, and take into account that these are so-called disjoint sets, and we're going to note them by this graphic axis that we have over here, which are disjoint subspaces of the total feature space. And disjoint means, of course, that essentially at the moment that we are, say, in this particular first x0 that we have over here, then you cannot be at the same time in x1, and that of course makes sense. That makes sense based already on the definition that we have over here, because of the fact that we should realize that suppose that, for example, we are going to be in x0, which means that the probability of y equal to 0 is going to be, condition of course on x equal to x, is going to be, well, strictly higher than the outcomes of all the other situations. Well, then of course it cannot be at the same time that the probability that y is equal to 1 is also strictly higher than all the other potential cases. So therefore you should take into account that these are going to be disjoint sets, simply by the definition of this g star x that we have over here. That means, of course, that the the decision to in fact predict a particular class as we have it over here becomes very simple at the moment that the outcome of the feature set is going to be, well, say in a particular class or decision space xi, then we are simply going to predict y equal to I. Again, at the moment that we only have two different decision spaces, either the decision space of having no heart attack or one having a heart attack, that means, of course, that as soon as x is in, for example, x1, then we are going to predict a heart attack. Otherwise, we're going to predict no heart attack. The boundaries of these subsets are usually called decision boundaries, take into account that, of course, even though it is the case that these decision spaces are, say, they are disjoint in the sense that we cannot have exactly, well, two outcomes or two or more outcomes that are going to be having probabilities that are going to be larger than any of the other outcomes. So they cannot be strictly larger, but it can of course be possible that we are going to be at the boundary in the sense that at least two different classes have exactly the same probabilities and they are going to be highest. That's the easiest of course to explain at the moment that we again are going to look at the situation in which we have only two outcomes, say only heart attack or no heart attack, and that means of course that there could of course be a probability in which a situation in which the probability of having a heart attack is exactly equal to the probability of not having a heart attack. Well, that's of course possible. Then we are on this so-called decision boundaries. We denote these decision boundaries usually by delta Ix, for I of course again from 0 to c minus 1. These decision boundaries are sometimes also called discriminant functions and take into account that they are p-dimensional maps. Take into account that this still is a little bit fake, but it becomes immediately clear at the moment that we are going to look at a special case of c equal to 2. Then we should realize that then the decision spaces, there can only be two decision spaces in that particular case, of course, x0 and x1. Let's look at x1. Well, x1 is then of course determined by all those x's in the full support of x for which the probability of y equal to 1, condition x equal to x, is strictly larger than the probability that y is equal to 0, condition x equal to x. Take into account of course that we do already know that this probability of course is nothing else as 1 minus the probability that y is equal to 1. So that implies that what I can do is that I can bring this to the other side, and that implies that it's x1 is simply nothing else as all those combinations for which 2 times the probability that y is equal to 1, conditional x equal to x is larger than 1, and then of course we can write this as the probabilities needs to be larger than half. So that means that we are going to predict y equal to 1 whenever the probability is larger than a half. And that of course makes sense because of the fact that again at the moment that we're going to look at the situation of heart attacks, then you should realize that as soon as we predict that the likelihood of having a heart attack is larger than half, that means of course that the probability of not having a heart attack is smaller than a half. That makes it the best thing to do is to predict in this case a heart attack. Delta x is then of course implicitly defined by all those combinations of the x's that we have over here for which the probabilities are exactly equal to each other, and that of course means that these are all the combinations for which the probability that y is equal to 1 is condition x equal to x is equal to half. Of course that's also the probability that y is equal to 0 is equal to a half. The rest of this video I would like to use for looking at a particular simulation. However, in order to make that particular simulation, what I need to do is that I have to go for an intermezzo, and these are so-called mixer distributions. I'm quite sure that you might not have seen any mixer distributions in your life before, so therefore I have to first of all introduce them. And in order to introduce them, I would like to say that for complex simulations, statisticians often use so-called mixture models. As an example of such a model, suppose that we have the following random variable. We are going to denote that by x, and for a pi in between 0 and 1 we are going to denote it by or we're going to define it as x is equal to pi times u1 plus 1 minus pi times u2, where u1 and u2 are now going to be independent random variables. We should realize that this is just a definition of this x that we have over here. Well, then it's not so difficult to show, that is simply based on standard probability theory, that the density of x, at least if u1 and u2 of course are going to be having density functions, so they must be continuously distributed, then the density of x can be written in the following format, namely fx, evaluated of course in x, is equal to pi multiplied by fu1x plus 1 minus pi times fu2x. So it's simply nothing else as well the weighted average of the two density functions that we have over here. Even though this of course makes a lot of sense already, it's also not so difficult to actually prove this thing that we have over here. As an example, suppose that u1 and u2 are going to be one-dimensional, normal with means equal to mu1 and mu2 and a common covariance sigma squared. Then at that moment in time, the density of x is going to be equal to, well, pi times, well, the standard normal density, evaluated in this case in x minus mu1 over sigma, multiplied of course by 1 over sigma in order to, well, normalize or to standardize this normal distribution that we have over here, and plus 1 minus pi times also a standard normal density, but now evaluated in x minus mu2 over sigma, multiplied by 1 over sigma. And well, the nice thing is that then we can look at a simple picture. Here we have on the x-axis, we have the different values of x, starting here at minus 2 and ending here at 4. At the y-axis, we have the outcomes with respect to density function. And what we're going to get is a very nice bimodal density function that we've over here. And it should not come to you as a big surprise that if we are going to take mu1 equal to 0, mu2 equal to 2, and sigma equal to half, that then at that moment in time, and pi is by the way equal to 0.3, that we are going to have two modes, of course, one in this 0 that we over here, which is exactly equal to the first mean of our normal distribution, which of course also the mode of that particular normal distribution, which is equal to the 0 that we've over here, of course, and the second mode that we've over here is equal to 2, which is equal to the second mode of, or the mode of the second distribution, normal distribution that we have introduced on the previous slide. And another thing that we see here is that actually the probability mass around 0 is much smaller than the probability mass that we have around this 2 that we have over here, and that of course has everything to do with this pi that we have over here, which is only equal to 0.3, which means that more or less 30% of the probability mass is around here, and 70% of the probability mass is around here. So that is the whole idea behind this mixture distribution. The nice thing with respect to mixture distributions is that it gives us the opportunity to get bimodal densities, and that is of course very helpful because of the fact that if we look at the standard densities that we know of in probability theory, they usually are unimodal. So at the moment you would like to get bimodal densities, then you should use mixture distributions. However, this is a very simple mixture distribution. Of course, we can extend this very generally to a so-called p-dimensional mixture distribution of, say, k random variables. So the dimension then of the u's, they are going to be p-dimensional. We're going to assume that the u's are going to be independent from each other. And then our x is simply defined as the sum over all the different k's that we've over here, multiplied by pi I and multiplied by ui, where of course the sum over the pi i's, that must be equal to 1, and of course also the pi i's all have to be larger than 0. Well, then again you can prove that then the density is going to be nothing else as, well, the density of fx is then going to be nothing else as the sum over, say, the pi's multiplied by these densities that we have over here. Take into account that mixture distributions are actually very fruitful in economics. Take into account that, of course, econometrics and economics are somewhat related to each other, and take into account that, well, in economics, actually mixture distributions can be very practical because of the fact that we often do not know some underlying characteristics of an individual, and hence their outcome variables are sampled from different distributions. Take into account that at the moment that we, for example, are going to look at individuals and we're going to look at their wages. Well, wages are of course determined by a lot of things that we can observe, like the gender of the individual, the race of the individual, say the education of the individual, where the individual lives, and maybe some other characteristics. but there are also a lot of characteristics that we do actually not know of. These are usually the talents of the particular worker. And we should take into account that, of course, people could have many different talents. And therefore, it's very unlikely to be the case that this will give us a unimodal distribution. So therefore, in that particular situation, mixture distributions can be used. And an example of the use of mixture distributions in econometrics are the so-called mixed proportional hazard rate models, usually called MPH models. Well, that is something that you probably haven't had yet, but if you're planning to do a master here at in econometrics here at this University of Groningen, then there is somebody called Gerard van den Berg. That's one of our top professors at our university, and he actually will introduce duration models. Also will introduce these MPH, mixed proportional hazard rate models. I would like now to go on with a simulation example, and in this simulation example I'm going to assume that we have two different classes, and I'm going to call them red and blue. Of course, that is very abstract. We can of course think of any of the examples that we have seen before where we only had two different outcomes, like for example the heart attack example. Then at that moment in time, red would be a situation in which somebody is going to get a heart attack, and blue means then that somebody doesn't get a heart attack. We can also think of the situation of a face in the picture or not. Then red could be a face in the picture and blue could be no face in the picture. And we can finally think of situations in which we are going to think, for example, of credit worthiness of customers of a bank. Then red means that you're not credit worthy, and blue means that you are actually credit worthy. Well, then in addition that this is of course then the outcome variable, but we are also going to look at the so-called features. We're going to assume that the features here are two-dimensional, so there are only two different dimensions, and we're going to denote the different features. Well, the features are of course going to be denoted by x, but the different features that we have are going to be denoted by x1 and x2, and the realizations are going to be equal to little x1 and little x2. We're going to assume that the x's are going to be sampled from a so-called mixture of normals for both classes, but with different mixture distribution. I'm going to say much more about that on the next slide, and that means are going to be also sampled from different distributions, and we are going to have common variances. From the above, this means of course that based on the things that we have said about mixture distributions from this slide that we've over here, it means of course that P is equal to 2, the number of features that we have is equal to 2, K is equal to 10, and all the pi i's there are going to be equal to 1 over 10. And finally we're going to have a sample size of both red and blue that is going to be equal to 100. Then the calculation of the theoretical decision boundary can be done actually numerically. I'm going to say much about that later on, but we can actually calculate the theoretical decision boundary can be done numerically, and the lowest possible risk that we can ever get is equal to 0.1856. This is also something which you might not directly see how I actually calculate this, but this is actually also based on actually numerical calculation. In order to explain everything a little bit better, first let's look at the values of mu x1 and mu x2. So what I already said, I'm going to, this is also actually, these values are actually also sampled from also normal distributions, but different for blue and red. And we are going to have then mu x1, mu x2 for blue. And also we have exactly the same thing for red. And of course, since we have k equal to 10, we're going to have 10 different values for mu x1. These are the ones that we have over here. And here we have them actually for mu x2 for this blue that we have over here. And we do see that actually they're sometimes quite different from what we actually get from the reds, because of the fact that here we have 1 and there we have minus or almost -1 that we have over here for red. So take into account that blue and red, even though they are both from say mixture distributions with p equal to 2, k is equal to 10, and pi I is equal to 1 over 2, well, they are actually quite different from each other in terms of the axis that they actually will get. And well, based on this mixture distributions, what we can do is that we can actually sample reds and blues. So I'm going to do it here a little bit different from what I did in the previous simulation study, where I actually first of all I was well, in fact, sampling axes, and then based on those axes I was going to get outcome variable. In this case I'm going to assume that I already do have 100 outcomes of red and blue. The only thing that I actually need to have is in fact the corresponding axes that are from this red and blue. So I'm going to assume that I have 100 reds, and the only thing that I actually need to have is the related axes that are from the first red observation that I have, the second one, etc. And that I actually did in this slide, or this graph that we have over here. So here, to explain this, we have here again on the x-axis we have the different values of x1, we have here the different values of x2 here on the y-axis. And what I simply have done is that I first of all have simulated 100 different red points, and that implies that for example this point that we have over here actually had an x1 that was a little little higher than -1, and a little higher than this -2 that we have over here. But I have done that 100 times, so then I had all these 100 combinations of x1 and x2 for the red outcomes, and I also have done that with respect to the blue outcomes that we have over here. Well, and then what I'm going to do as well, or what I have done at least in this particular figure, is that I also have already calculated the so-called theoretical decision boundary. Question of course arises how I was able to do that. Well, this cannot be done in a closed format, so this cannot be done analytically. I had to do this numerically, and the way I actually did that was that I actually did nothing else, is that I made a grid here of 10,000 different points over here and 10,000 different points over there, and I asked myself for every point whether the probability of having a red was higher than the probability of having a blue. So what I did was that I simply started here in the left upper corner that we have over here, and I asked myself for the first combination of x1 and x2, I would say the first pixel of x1 and x2, asked myself the question, was the probability of having a red higher than the probability of having a blue? If that was the case, then I'm going to have a red pixel over here, otherwise I'm going to have a blue pixel over there. But in this particular situation, if I'm really here in this upper left corner, then actually probability was higher for red than for blue, so this is a red pixel. And what I did was that I just simply first of all did that along the x1 axis. I increased the levels of x1 and was first of all having here a row of all red pixels. In all the cases the probability of having a red was higher than the probability of having a blue. But then of course I went down over here, did exactly the same over there, and I essentially did that for any kind of pixel. And it implies that in the end what I found out was that in this left area that we have over here, well, the probability of having a red is higher than the probability of having a blue. In this area that we have over here, it's also the case, but in this I would say area here, more in the middle, we actually have that the probability of having a blue is higher than the probability of having a red. And that implies that well, on this decision boundary that we have over here, that is the optimal decision boundary. It implies that if we are in a blue area, then at that moment in time we should actually have a prediction to be blue, and in a red area we are going to have a prediction that should actually be red. And take into account that even at the moment that we're going to use the optimal decision boundary, so we're going to follow the optimal decision rule, then even in that particular moment in time, we can sometimes be wrong because of the fact that we do see that, for example, we do actually have a lot of red dots here in the blue area. So at the moment that, for example, I'm going to predict this point that we have over here, then I would actually, since it's in the blue area over here, I would predict it to be blue, but in fact this is a red dot, so therefore I make an error here. It's also true for all these red dots that we have over here, and it's also true for some of these red dots that we have over there. But take into account it's also the other way around. There are some blue dots in red areas, so this one, that one as well. And here also we have 2 or even 3 different blue dots that are actually in red area. So that implies that even in the case that we're going to follow the optimal decision rule, then we sometimes make errors. And the errors that we're going to make, in our case, is as already calculated, that could also be numerically calculated simply by looking for not just for 100 reds and 100 blues, but we can do this of course a million of times and find out what is the percentage of times that we actually make an error. We can then calculate that actually in roughly 18.6% of the cases we still make an error. And take into account that this actually, we cannot do anything about that. And the reason behind that is because of the fact that we should realize that even in the case that we're going to follow the optimal decision rule, that means of course that even though of course, well, this is a red dot, and even though we do know that because of the fact that this red dot is in the blue area, it means of course that the likelihood of having a blue is higher than the likelihood of having a red. We should realize that that doesn't mean that in this area over here, the likelihood of having a red is equal to 0. It only means that the likelihood of having a blue is higher than the likelihood of having a red. But of course, it could be just a little higher. It could be the case that in this area over here, the likelihood of having a blue is say equal to 51%, and there is a likelihood of 49% that we have a red over here. And therefore still you can actually have a lot of reds in this area over here that are actually officially in a blue area. So take that into account. Now an important question that arises is, well, based on what we had at the previous slide, we did already have the, say, optimal decision making rule, namely this decision boundary that we have over here. But take also into account that in practical situations we do of course not know this optimal decision boundary. So the question arises, how could we actually try to estimate it? Well, there are many methods that can be used in order for estimation, and even though the book actually does have a lot of them, it has logistic regression, which actually you do already know quite a lot about as econometricians, but there are also other methods like discriminant analysis and maybe also some other methods. But take into account that most of those methods actually don't predict so well, especially in comparison to the methods that we are going to look at later on during this lecture series, like for example the trees as well as the random forests. These approaches, they are actually much better in able to predict in the case of classification rather than the methods like discriminant analysis. So therefore I'm not going to discuss them over here. However, there's one fine method that can still be used, at least at the moment that the the dimension of the features, so if you do not have that many features, can still be used and actually works quite well. And it's a method that you have already seen before because of the fact that that's the so-called the method of nearest neighbors. But take into account that the method of nearest neighbors works a little bit different from the continuous case, but the idea is exactly the same. Well, in the case of nearest neighbors in classification, well, then still what we're going to do is that we're going to look at the, say, observations that are closest, in this case, k nearest neighbors. But in this case, we're going to do a little bit different in a sense that, well, in the standard continuous case, we're going to take the mean over the outcomes. That is not what we're going to do because of the fact that that doesn't work in classification. Instead, what we're going to do is that we're going to, well, choose that particular class that has the highest frequency among the k nearest neighbors. That actually occurs most among the k's nearest neighbors. So that means that essentially what we're going to do is that we're going to look at the percentage of times that a particular class is going to occur in a particular, say, class of k nearest neighbors, and then we're going to take that particular class that has the highest frequency. Well, in order to explain that even a little bit better, maybe the best thing to do is to go back to our example. So suppose that we are again in this example where we have on the x-axis the different values of x1, and on the y-axis we have the different values of x2. Then we do already know the optimal decision boundary. That is this one, this dashed line that we have over here. And we do already know that in the optimal decision boundary, what we need to do is to predict here red as well, and here in the middle we have to predict blue. But the question arises, how can we do that with respect to nearest neighbors? Well, let's set in this case k equal to 15. I'm going to come back to that later on, why I've chosen k equal to 15. But that essentially implies that for any point that I'm going to have, for example this point that I have over here that I would like to predict, then what I can do is that I can find the, say, 15 nearest neighbors that we have over here. And at the moment that we are going to find more, say, blue dots than red dots, that means of course that we have 8 or more blue dots in comparison to red dots, then at that moment in time I'm going to predict a blue, and otherwise I'm going to predict a red. So what I've done now again is among all the different pixels that we have over here, 10,000 by 10,000, what I simply did was that for any particular pixel I have asked myself the question, well, what about the 15 nearest neighbors? Well, in this case those are all red, so that means that in this area we are going to have a red outcome, and I have done that for all the different pixels. And if I do that, then I actually get this picture that we have over here. So then the decision boundary, essentially the estimated decision boundary, is this one that we have over here. It implies that I'm going to predict here blue in this area that we have over here. I'm going to predict red in this area that we have over here, and red in that area over there. And we see already that we do actually quite a well job. Again, that is not because of the fact that we predict so many of the blues correctly or so many of the reds correctly, but it's because of the fact that the difference between, say, the optimal decision boundary, this dashed line that we have over here, and the estimated decision boundary that we have over here, well, they don't look so different from each other. The only place, of course, where we have the problem is this area that we have over here, but take also into account that that might be a problematic area because of the fact that we do already see from the number of reds that we have over there that most likely the probability is of course higher for blue than for red, but probably the differences are very, very slim. Well, then we already see that we do actually quite well in the case of k equal to 15. That's not completely by coincidence. The reason behind that is because of the fact that what I have already done is cross-validation, and based on cross-validation I actually did find out that k equal to 15 was the best outcome. If we take k equal to 50, well, then we don't have such a great outcome because of the fact that then we get this picture that we have over here, and then you immediately see that actually this is not such a great predictor because of the fact that we do see that here we have a lot of, say, we actually predict here blue, but in reality what we had to do is of course to predict red. Also here, this whole area that we have over here should be red, but it's predicted to be blue, and we also see, even though that's probably not as problematic, we do see this area that we have over here as well as that area that we have over there. So we should realize k equal to 50 is not as a great predictor as k equal to 15, but take into account that that's actually also the case at the moment that we set k equal to 2, well, even though that's a little bit more difficult to see over here. But take into account that at the moment that we use k equal to 2, then actually we're going to get, well, corresponding problems as what we also had at the moment that we were looking at continuous case. Then we're going to see that what we essentially would like to do is then to, in fact, create very small islands around, say, these red dots that we have over here in the blue area, simply because of the fact that we try to predict the things that we observe. And That means essentially over smoothing, over predicting in this case, and that is in fact not a great thing to do.